Hello everyone, my name is Francesca Naretto and today I'm presenting to you a work entitled Predicting and Explaining Privacy Risk Exposure in Mobility Data. This work was done with Roberto Pellungrini, Monreale, Franco, Nardini and Mirco Musolesi. So the main topic of this work is the privacy risk assessment. The goal is to assess the privacy risk of each user in a dataset, and right now it is really important to do so because it is also a requirement of the General Data Protection Regulation in Europe. There are already some traditional algorithms that are able to assess the privacy risk, and in particular we refer to Prudence, that is a state-of-the-art framework for the privacy risk assessment and the privacy risk mitigation. To assess the privacy risk of the users in a dataset, Prudence simulates a privacy attack. So it assumes that there is an adversary that wants to know something more about the dataset under analysis and has also some background knowledge information he may exploit to know something more about the dataset. And in this setting, mathematically speaking, the privacy risk of the user is actually the probability of being re-identified by the adversary. And so to compute it, we have to consider all the different background knowledge configurations the adversary may have. But this means that we have to apply a combinatorial calculus that is expensive and time-consuming. So for this reason, we would like to overcome this limitation by proposing the use of machine learning models to predict the privacy risk. In this way, we are going to be faster because we do not have any combinatorial computation to do, and we are going to be online in the sense that when a new record arrives, we just have to feed it into the machine learning model, and then we are going to have on the fly a result, and also user-centric. This is actually different with respect to Prudence because Prudence requires an entire dataset to evaluate the privacy risk of people, and this is because Prudence was in a company setting, let's say, in which the company has to understand the privacy risk of the user in the dataset to use the dataset as an entity. But in this case, we would like to give to the final end user his result, and that's all, his privacy risk. But even if there are several good things in using machine learning models, there is a limitation, that is, how can we interpret the result? In fact, we would like to give to the end user a list of the reasons that led him to that particular privacy risk, but it's not easy to do so with machine learning models. For this reason, we propose Expert, that is a framework for the privacy risk prediction and privacy risk explanation. So this framework has two different components. The first one is the privacy risk module that exploits machine learning models to predict the privacy risk of people. And the second one is the risk explanation module that exploits explanation methods, agnostic and local explanation methods, to give to the end user an explanation about the reasons that led him to that particular privacy risk. So, Expert step by step. We are starting with a sequential dataset, and in particular we are working with mobility dataset, so trajectories, and we simulate on this dataset a privacy attack, as the ones that I told you before of Prudence, so the traditional combinatorial ones. But we have to do it just for one time because we need to obtain the risk vector. Well, after this first phase, we are going to have a label for each user that our machine learning model can be trained on. So this is actually an important step. Then we have to extract some features, and in this way we are going to obtain a feature-based dataset. These are actually the features that we extracted for our experiments. So at this point we have a tabular representation of our users, and we have a label for each user. So we are finally able to train our machine learning models, and in fact we can finally predict the privacy risk of people and also explain it using explanation methods, and in this way we can also increase user self-awareness. So To assess the methodology we proposed, we conducted several experiments, and we did so by using a real human mobility data set that was transformed in two different ways, obtaining two different data sets, one called ISTAT and the other Voronoi. For the ISTAT dataset, we applied to the trajectories a generalization based on the tessellation of the Italian National Statistic Bureau, while for the Voronoi case, we applied a cancellation driven by a Voronoi division of the region, driven by popularity of the territory. So the two plots I'm showing to you are actually the distribution of the lengths of the trajectories for the two different datasets. And you can see that the ISTAT dataset has shorter trajectories with respect to the Voronoi case. So on these two different datasets, we applied our machine learning models to predict our privacy risk. And in particular, in the first table, you can find the prediction performance of the ISTAT on the ISTAT dataset, and in the second table on the Voronoi dataset. We applied 4 different machine learning models. The decision tree and the logistic regression that are actually transparent model, and the random forest and the geek forest that are 2 ensemble methods. So as you can see, actually the random forest and the geek forest are the ones that are predicting better. And in particular, the geek forest is the best one if we consider the ISTAT dataset, that is the one that has a greater imbalance between the classes. This means that geek forests are really robust with respect to highly imbalanced classes, and since this is actually a setting in which there is a huge imbalance between the classes, these are the perfect choice for this setting. Then we also applied some explanator for the second module of our expert framework. And all the explanator we considered are agnostic, because we would like to consider the first module, in this case, as a black box in which we do not know what is implemented inside. So we decided to apply Shap, that is a feature importance agnostic and local explanator, that is giving us explanations like this one, in which the pink line is actually representing the importance of each feature for a particular record. And also we applied Lore, that is an agnostic local explanator that is output logic rules. And this is the same record explained by Lore. So we have a set of premises and then the actual class predicted. After this first phase, we decided to analyze a little bit more the difference between Lore and Shap, and also between the transparent models. So with respect to the transparent models, we considered Shap with respect to them. And in particular, we wanted to see what are the most important features for the different models for the prediction phase. And we found out that geek forest, decision trees, and logistic regressions are found that logs, that is the total number of locations visited by the user, is actually the most important one. But this is not true for the random forest, that instead is selecting the sum, that is the sum of the lengths of the different trips the user did. So actually, as you can see here, there are similarities between the 4 models, but there are also some interesting things, like, for example, the fact that the entropy of the users' home and work locations are actually seen as important only for the logistic regression model. Well, then we also decided to compare Lore and Shap, and we did it using the Jacquard similarity and the coherence index. The Jacquard similarity is simply telling us that actually the intersection between the features of Shap and the features of Lore is really small, so they are not really similar. And the same thing is the one of coherence, because coherence is telling us that the important features for Lore are not really important for Shap, and vice versa. So this is actually an interesting result, because it highlights a lot of differences between these two methods. So to wrap up and conclude, we propose Expert, that is a framework for predicting and explaining the privacy risk. For the prediction phase, we found out that the Geek Forest is actually the best one, that is able to handle the imbalance between the classes. And we also found out interesting results for the local explanations, even if there is still work to do and other analysis to fulfill. The main limitation of our approach is the fact that we have to define and extract some features, and as a future works, we would like to use models that are able to work with sequential dataset and also extend this work to generic sequential data. Thank you for your time, and if you have questions, please ask.